All right, welcome everyone. Week 10 of IS50B, in which case you get a masterclass in computer science. C++ 20 coming on strong. So if you have a struct, you can generate a less than, an equal to, a not equal to, greater than or equal to, less than or equal to, greater than operator in one simple trick the doctors hate, which is by doing this. And so this will allow colors to be compared, less than or, and how will it know if one color is less than another color? It does so in lexicographical order. So the reds are compared first, followed by greens, followed by blues. In this case, we don't really care about them. We just care about the equals and not equals. Okay. So down here, we are going to have a world of tiles again, and we're going to accept mouse clicks from the user and put a dot on the screen everywhere they click, and we're going to draw a line between them. And when they're done, we'll finish up the last line, and it's going to be your job to draw triangles between the points, and you're going to turn a polygon into a triangle. Okay. We'll talk about how to do that in a little bit. Let's just go through the code. If you are not a C++ person, then partner with someone who is, so you can get it done. All right. So printing the world using colors for colors H. So this is going to loop over every spot on the screen, and it's going to remember who the last color is, so that we don't have to constantly spam our network connection with change the color to black, change the color to black, change the color to black. Instead, if the last color we put out was black, we should do a set background color as well. Set the foreground color to black. We're going to set the background color to black as well. Then background to black as well. Then we're going to loop every point on the screen. If that point has a different color than the last one we outputted, then we call set background color, which will output to the network, change the color to this RGB value, whatever is there, and it will then remember the last color that it outputted. Okay. And it'll keep doing that until it finds a different color, in which case it'll change the colors again. That should work. We are not doing Delaunay on this assignment. Go away. We're not doing Lloyd relaxation. Go away. We're not doing winners. Go away. We're doing polygons. Okay, we don't need SRAM time, I don't think. Using terminal size, yeah, probably should do that. Removing one from the rows so it doesn't scroll off the top of the screen. And then it sets the world to be the number of rows, the number of columns. We don't need that anymore. We're not loading cities anymore. Do a Delaunay calculation. Don't care about you anymore. Okay. So what we need to do is enable mouse events. Enable mouse events. Dang it, that was just in the code I erased, huh? Yeah, fine. Then Delaunay 2.reference main.cc. Come right back in here. Quick read mouse. Did I not do this? I thought I did that. What was the assignment where we read the mouse clicks? Which one was that?
Oh no, edgelord.
Edgelord, that's right. Thank you. Okay. Edgelord. Reference. Mouse. Okay. Mark X. Yank to X. Edit main.cc. And go. That did not work. Did that work? It didn't work. Undo. Paste. There we go. Okay. Turn on low rent and curses mode. So part one will be read mouse clicks until the user hits space to finish. Print the world, click on two provinces, one to attack, one to... So click on the screen to add a point to a polygon, space to be done. Row equals last row, click column equals last column, int last row is -1, 0, no. 0, last column equals 0. All right, so while they are the same, don't do anything. I'll set it to -1, I guess. So it's going to sit there in loop over and over again, and if they ever type in a space, then it will break. Attack a row equals last row. Attack. So move cursor to here, and we will add a X to that spot. Okay. Now we need to add to the points database that point. So, should really be a vector too, shouldn't it? We're not doing 3D stuff here, we're doing 2D stuff. There we go, and alright. We don't need the defender at all. What's up, girl? Attacker row, defender row. Continue. Don't care about that, don't care about that, don't care about that, don't care about that.
Can you order some food?
You want some food? Here, DoorDash app. Okay. So let's see if this works first of all, and then we will make a data structure that holds all the points. Well, we already got it, we'll just add to it, and then we'll see how that works. Get terminal size in ioctal? No, it's in it's in color setting. Which is based on ioctal. What would I like? Pizza? Pasta? Okay, so let's get this going. Main.cc. No need to link in curses. Mouse handler not declared. Did you mean mouse mode? Oh, yeah. We do need a mouse handler, don't we? Okay. So what are we going to do here? Attacker. Oh, these guys don't exist, do they? Okay. Let's see. Make these globals. Yes, girl. I'll just copy that whole thing over.
I can't find the pasta section.
You can't find the app?
I found the app. I can't find the pasta section.
Can't find the pasta section. That should work. Let's double check. Attacker row does not exist. That is correct. All right. So click, 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 click. Not do anything. Why are you not doing anything? Oh, because we're not writing anything into the database. That's why. Okay. All right. So we need to write into the world the color. It's writing an X, but then it's immediately going to print the world, which refreshes it. Okay. So we don't need that at all. We don't need you either. Instead, we're going to say world.at click row dot at click column is equal to 255, 255, 255. We'll just make it white. And we need to add to the points database as well. Points. In fact, let's not make this X and Y. Let's just make this row and column. And we'll just make that an int for simplicity. There we go. All right. Points dot push back click row click column. Points is a vector of vector 2's. It's a struct with row and call. Points up pushback. Needs a parentheses. Click, 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 click. Do I need to refresh the screen? Probably not. Maybe for print world, we don't refresh the screen. There we go. Less flickering. Okay, so given a polygon, given a polygon, you need to triangularize this. So you are going to have to fill this thing with triangles. So you're going to be given a point cloud, and you're going to connect the lines to make triangles out of them. Okay? Looks much nicer without a refresh. Yeah, I agree. So if you want to do Delaunay triangularization, which is a nice way of doing triangles. Technically, you can take any 3 points and say they're a triangle, right? But is it going to look good? I don't know. And also, you can't have a triangle if it has another point inside of it. That's when you're triangularizing. Like, you can't just go this guy, this guy, this guy, because all these other points are going to be interior to it. You can't do that. So, do you guys remember how to see if a point is inside of a triangle? You guys still have the code for that? So this is the code I'm going to push out to you. And so basically, the input is just going to be a bunch of clicks, and then you're going to draw on the screen lines connecting them. And I might even give you guys some code to do lines. I don't know. Do that in a second. So, let's take a look at this. IS50B, new page, 31921. So if you have a point and a point, and a point. That's a triangle. And you've got another point here. You cannot have that triangle there. You cannot triangulize this mesh like that. It's not allowed. And you can test for that easily by just taking the dot product. Remember that, or the cross product. So if you take the cross product of each of the lines of the triangle, if the vector result, if the cross product result is negative, it means it's to the right, depending on which order you do the operations. And so this would not be a valid triangularization. Okay. So how do you go about doing it? You got these 4 points here. How do you go about doing it? Well, one approach you can take is you can just sort all of the points left to right. You know what I mean? And so you take the first one, connect to the second one connect to the third one, right? You know what I mean? And then second to the third to the fourth, right? Because if there was another point down here, well, then it'd look like that, you know, and then these guys would be connected. You're going to get a really ugly triangularization, but it would work, you know. I'm not going to enforce which triangularization method you're going to use. So if you want, you can just sort all the points. Sort points left to right if you want. It's a pretty common starting place for a lot of these algorithms. You sort them. But what you do with Delaunay is you kind of take groups of 4 points at a time, and you see if you take the longest edge of the triangle, in this case here, and you see if anything is within the circle of it. So let's see, let's do an example. So points left or right. Right. Okay. So let's say you've got this guy here. Okay. So let's say you try making this triangle here. What you do is you take the longest edge of the triangle and you do a circle, right? And if there's anybody that's within that circle, then you can't. Let's say this one's outside, just for the sake of convenience, but this guy's inside. Then you can't, then that violates the Delaunay principle. And what you need to do is you need to flip this line. So you switch it from being this way to being this way. And that gives you a much nicer looking triangle. The other triangularization works, like it is technically a triangularization. Like you could triangulate it. Let's move this guy a little bit further out of the way. You know, you could, this is, you know, this is valid, right? You understand? Like that's, you got 4 points, you got 2 triangles, cool. None of the points are interior to the triangle, cool. But it creates these weird long strips. And these things cause problems when you're doing computer graphics because, you know, what if the triangle is, you know, works out to be less than a point, or you got these, you'll get weird mirage effects and things like that out of it. So the Delaunay property says you take the longest edge of a triangle, you sweep a circle around it, and you see if that guy is inside. You know, if you're looking at this triangle here, you see if that guy is inside of our radius. If it is, then you switch that. So that line switches to here. And then you get a nicer triangularization. However, for this assignment, I don't care. Okay. So if you want to output it that way, or output little shardy triangles, I don't really care. It's a recurring theme that I have that I just want you guys to get something going. Get a triangularization working first. Get a Voronoi. Get a whole algorithm working first, and then after that, work on it to tweak it. The most important thing is just getting that first step, getting an answer out there. Okay. Make it work first, then make it work well, then make it work fast. Yeah, exactly. So in CSI 45, I give extra credit for speed. I don't usually do that in earlier classes, you know. So that is that's that. So one interesting thing. So let's say we've got one interesting thing here. Let's say we've got this Delaunay triangularization. is that if you take the center point of the Delaunay triangles, this is actually used for a Voronoi. This is actually the Voronoi. The Voronoi region, domain, the Dirichlet domains of Voronoi regions, and Delaunay triangularizations are actually paired opposites of each other. So, let's see. I think there's a picture of it. Wikipedia somewhere. Yeah. So the Voronoi region is in red here. Yep. Connecting the centers of the circumcircles. Yeah, so you can use the Delaunay triangulation to make a Voronoi, and I think vice versa as well. So, it's the dual graph is what it's called. I am speed. Okay. Yep. So that is our homework assignment. Oh, how do we? Oh, I know JT wanted to talk about rasterization. Is JT still here? No, he left. Really? Harlan was here a second ago, wasn't he? His internet died. You wanted to hear about it too? Yeah. Okay. We are recording, I believe. Prado, were you interested in rasterization? Rasterization. All right, cool. Let's talk about rasterization. Rasterizing. Such a cool sounding word. Like JT was saying that he was reading Carmack's blog or something, and he used the word rasterization. He's like, I don't know what it means, but it sounds cool. So basically, rasterization means putting pixels on the screen, right? So given a set of triangles, how do you determine what pixels to draw on the screen, right? Because a triangle is oftentimes represented using a double. And if we just have 2D triangles, you think it's pretty easy, right? Like you got these triangles. But what happens if a triangle partially covers a pixel, right? That's where it gets a little tricky. So usually we take the center point. And so you say whatever the center point of the triangle is, if that's within a triangle, like you can see the center point here, that's within the triangle, that's the color it gets. Okay? And so that works for triangles, works for lines, rectangles, whatever. So let's do some rasterization. So that's how you convert from a line to actual putting pixels on the screen. And in 3D, if you have a rotating triangle in 3D, you have to project that 3D triangle onto the 2D space of the screen. And then see for every pixel on your screen, is that pixel within the triangle or not? If it is, draw using the color of the triangle. And the color of the triangle could be based on the light, the texture, material properties, all that kind of stuff. So it's a big graphics pipeline. Yeah, here we go. Application moves geometry around. Geometry is a bunch of triangles, and they get rasterized. Okay, so in 3D, we should probably talk a little bit about 3D, even though we're not going to do 3D. We're going to do 2D. Let's talk about 3D a little bit. So let's say that you've got a person. Got a person. There's an eyeball, right? That's an eyeball, I guess. And it's looking at this world, and there's like a house or something. Be in awe of my art skills. Okay. So there's back here, I'm going to represent with dots. There's more triangles. We can't see it though. We're looking at kind of the front of the house, right? So there's triangles in the back here we can't see. And so those triangles are going to get back face culled. Do you guys remember that? That if you have a triangle, the direction you order the points in the triangle determine if it's facing forwards or if it's facing backwards. Anything that's facing backwards by default is not drawn. Do you guys remember that? It's called back face culling. Yeah. Sometimes for really thin objects, you might do two-sided triangles. Like if you just have a triangle and it needs to appear on both sides, like for leaves and things like that, you might do two-sided drawing. So you can turn it on and turn it off, and you can also change which direction is forwards and which one's backwards. You thought it's called frustrum culling. Nope. This is backface culling. Frustrum culling is because your camera, your eye, the camera, has a frustrum. And a frustrum is a invisible pyramid with the top chopped off. And it looks kind of like that. It's invisible, though. You don't see it on the screen. Dang. Yeah, whatever. And so if you have another house, like over here, this house is not going to get drawn because the house is outside of the frustrum. And so your graphics pipeline will, when you're given a triangle to draw on the screen as part of rasterization, it will say, is this triangle within the viewport? So a viewport is a region on the screen where you got a camera, basically. Okay, so normally the viewport covers the entire screen, but not always. If you're in a racing game, let's say you're in a racing game and you've got cars in front of you and you're driving around. However, your rear view mirror up here might be a separate viewport. This might be viewport 2. And so that rear view mirror might actually be a camera attached to the back of your car. So you can have one viewport for the front of your car looking out, and then you can have another viewport in the rear view mirror, or the side view mirrors. Could also be additional viewports, things like that. But for simplicity, let's just say there's one viewport. The viewport will have a view frustrum associated with it. And that is, again, a camera. The camera has a frustrum, and the frustrum is a pyramid with the top chopped off. Okay? And so there is some terminology in a view frustrum. Something like that. You have what's called the near clipping plane. And anything closer to the eye, like let's say you have a leaf, and that leaf would like block 2/3 of the screen, you don't want to draw it. And so anything closer than the near clipping plane doesn't get drawn. Okay, so that is frustrum culling. Okay, so anything closer than the near clipping plane does not get drawn. Anything to the right or to the left of the frustrum gets clipped. It does not get drawn. You don't bother rendering. Because remember, we've been talking about cross products and things like that. Graphics cards are very fast at doing that. And so if I give you a triangle and the graphics card's like that triangle is not within the frustum, throws it away. Go on to the next triangle. And so there is some cost with, at least having to go through all the triangles. The rendering pipeline is throwing at the video card, but the video card will very quickly be like, nope, nope, nope. Okay, you're in here. Okay, so you're in here. It is further away than the near clipping plane. It's nearer than the far clipping plane. And you've got the FOV. The FOV is the angle. That's a really ugly theta. Whatever. That's whatever. All right, the angle. The angle there is the FOV, right? How wide the frustum is. And so it does frustrum culling. It does backface culling, which gets rid of all the backwards facing triangles. It's very simple. You dot product, you cross product. You cross product two of the numbers here, and you can tell, is the normal facing me or is the normal facing away from me using a cross product. If it's facing away, you don't draw it. Okay, so frustrum culling is just, I'm not looking at its direction, or you're looking at its direction, but it's too close, or you're looking at its direction and it's too far away. And we hide the far clipping plane with fog, right? So rather than having geometry just appearing as you're walking towards it, bloop, 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 we hide it in different ways. In Animal Crossing, is that it? Yeah, Animal Crossing. The world is round, and so as you're walking, the world kind of goes like this, so it can hide things further away. In multiplayer games, everyone's client is doing this every tick. Yes, this is every frame. It is doing a render. So you've got a bunch of geometry in the world. And that geometry is oftentimes culled in advance by the rendering engine. So if you're in Unreal Engine and you're in like some big outdoorsy scene, like you got like mountains and stuff like that, right? And you're here and you're looking this way. Maybe there's more mountains further away that it won't draw because it knows you can't see it. Or there might be visibility culling, where like if there's a wall here, then it knows you can't see the stuff back there, so the engine will cull it prior to even being tossed at the video card. There's a lot of steps that are designed to shrink the number of triangles going into that rendering pipeline. You guys with me on this? And so there's stuff called like level streaming. So with level streaming, you can load and unload chunks of landscape. So you're walking towards this landscape, it'll load, and the landscape over here will get unloaded using level streaming. I know Walker and Sibilia have done that before, right? So as you're walking around, it will load more tiles in the direction you're walking, and it will unload the stuff back there. It's too far away to see now. So typically these things are organized in these giant tiles, and it'll load like one chunk of land at a time. And so you can have different buildings on it. And as you get close, hopefully your system is powerful enough that you don't notice it just popping in, right? Because it'll look really bad. So hopefully you got enough gas to kind of handle, enough tiles around you. But if you look off in the distance, oftentimes you'll see things bloop, pop in, and it loads things and it unloads things in order to keep the number of triangles you have to work with down. And then there's visibility testing. I'm just throwing lots of terminology at you right now. Potential visible set. This is a list of all. This is a vector or something, whatever it is. All triangles we might be able to see. Okay. So input, XY location, output, PVS. So the engine, this is something the engine will do. If you have pre-computed visibility turned on. Okay. So you have an XY, or in 3D, you have an X, Y, and Z location, and there is some data structure, and that data structure will return a potentially visible set of every triangle that you could possibly see. And then you cull, and then you cull it, and then you cull it, and then you cull it, and then you cull it. And so maybe step one is level streaming, and then all the stuff from the level streaming goes into a potentially visible set computation, which it's like, if you're in a room, like let's say you're in a maze, and you're standing here, you cannot see this way, right? You can't see that way. You can't see anybody over here. That's not visible. However, you can see these things in here, right? And so the PVS computation would return all of this stuff that you could maybe see, but all this stuff over here gets tossed. And so the watchword for today is, when you're doing rasterization, there is step after step after step to try to eliminate every single possible triangle that it is cheap to eliminate, right? So if you're doing level streaming, don't load the mountains on the other side of the world. Only load mountains within 2 tiles or whatever from where we are. Cool. Now, do PVS. This is more useful in indoor stuff. If you're in big landscapes, maybe you don't worry about it, because landscapes, you can kind of see everything, But if you're doing a lot of indoor stuff, then you do a lot of pre-computed visibility. And so with pre-computed visibility, pre-computed visibility, which can take a while. Like running a pre-computed visibility thing on Unreal Engine can be very expensive. Can take all night, right? Then that gives the engine the ability to do this. Given where I'm standing in the world, what can I see? And that throws away a lot of triangles, hopefully. And then from those triangles, we feed them into the Frustrum Culling, right? And so all the triangles we can see there, that one's to the right, can't see it. That one's to the left, can't see it. That one's too close, can't see it. That one's too far, can't see it. Okay, that one we can see. And then, that one's backwards. Throw it away. Throw it away, throw it away, throw it away. So you've hopefully gotten rid of 99% of all the triangles before you get into really the rasterization process. Are you guys with me on this? At the end of the day, what you're going to have is you're going to have the eye, and there's going to be some triangles. That's the front of the house, and then, maybe that's the barn. There's 3 triangles here, and maybe, there's like the roof. I don't know what's happening here. It's a roof somehow. Yeah, there's 2 triangles on the roof. And maybe those are the only 5 triangles you can see out of the billions in the world. And, but there's probably some landscaping here. Landscaping might be a couple of triangles as well here, and a couple triangles here. Whatever. So we've eliminated 99 billion triangles, and we're down to the 10 that we can see. Okay. If you ever played a game with an elevator or a ladder, usually that's used to hide level streaming. Yeah. The Unreal Engine 5 demo got criticized because there's a scene where she's squeezing through some rocks, and people were saying, well, that's where they're doing the loading there. And the reality was they're not actually doing it. Like, the game engine is fast enough to load things in real time, because Unreal Engine 5 is based on SSDs existing. And so in real time, it'll load a low-res version of an object, and as you get closer to it, it'll very quickly, in real time, stream in the increased detail, so you can walk right up to a rock and stare at it in all of its fine glory, and as you walk away, it hurriedly throws away detail. Oh, you're walking towards that rock, and it starts streaming in data on that, and it holds the data in a hierarchical format. So that things that are far away, you only have to load a little bit of the object. You can load 10% of the object, and you'll have a nice low-res version, and you walk closer to it, it streams in the next 10%, and it streams in the next 50%, and you walk all the way up to it, you can see every crack and detail in its full 4K glory for every pebble on the ground. Or at least that's the theory. It's not out yet, so who knows how it'll work in practice, but that's the general idea. So, does auto LED stuff? Yeah. Yeah, I'm psyched for it. If it works, who knows? I assume it will. They've got a pretty good track record. So, rasterization. So you guys understand what we've done so far? What we've done so far is the application moves geometry around, the house moves, the airplanes move, and then you do culling. There's lots and lots and lots and lots of culling. Right here. Right? All the triangles are projected and lit and clipped. Okay, so let's see. Projection, lighting, clipping, far clipping, near clipping. Yeah, it's going to figure out. Okay, so for every triangle, it's going to figure out where on the screen it's going to draw. And this is done using projection. So in Unreal Engine 4, there's actually a project node. But basically, there's a little bit of math you do that says, if this is my view frustrum like that, this triangle here, let me switch over into screen coordinates. So that triangle there, that's the front of the house. That triangle there is going to look like that. The landscape, there's a triangle here. There's a triangle here. And then the roof is going to kind of come down like that. Okay. And so all those triangles are transformed into screen coordinates. So remember how there is world coordinates and there are local coordinates. There's also screen or viewport. Viewport coordinates, which is what X and Y location that triangle is actually going to appear at. Now, rasterization takes place. For every pixel on the screen, it goes through and says which triangle is there. Okay? And it gets complicated if you have multiple triangles overlapping. For example, the roof here is occluded by the front of the house. Let's see if I can draw this better. So we got the front of the house here, and then behind it, let's see if we can do a 3/4 view here. Yeah, we'll just draw it like this. Okay, so if we're looking at it from the front, the roof is going to be occluded by the front of the house. And so we need to figure, so for this point here, let's say, it's not a very good drawing. Okay, so for the front of the house, we've got a triangle here, and then we've got the roof behind it. And maybe both of these guys, maybe that pixel there is both within the front of the house and the roof of the house. It's like when you're looking at it from the front, both the front of the house and the roof of the house are, that point is within it. So which one do you draw? Do you draw the triangle that is closer to the camera? Camera's over here again. Do you draw the pixel inside of the front of the house? Or do you draw that same pixel? We got a line coming through here, kind of. This is a weird 3/4 view. Do you draw the pixel corresponding to the front of the house, or do you draw the pixel corresponding to the roof on the back side? What do you guys think? Do you draw the front of the house, or do you draw the back of the house, or the roof, the side of the house, when you're looking at it from the front? You would think closest. You are correct. And so how you do that is interesting. It's an interesting question. And so back in the day, what they would do is oftentimes they would draw they would sort the triangles from closest, furthest to closest. And what you would do is you would draw the roof, which might look like this. Then I'll draw the front in blue over it. Let's see, shapes. Triangle. Color. Yeah. It's upside down. Triangle. So it'll draw the front of it over the roof. And can I make you solid? Can I make you solid? Can I make you solid? Order. Draw in front. Exactly. Can I make you solid? Can I make you solid? No. Whatever, it's solid. Okay, here, let me just fill it in. So it's they use something called Painter's algorithm. And so when you paint something, you paint the back layer first, right? And you paint over it. Okay. So you do this, right? And so what happens is you draw all of the pixels for the back thing first. So on the screen, you're rasterizing. Rasterizing means you're making a 2D array of pixels. And so it would draw all of the pixels corresponding to the roof first. So all of these pixels would get drawn in white, and then it draws over it with the blue. Let's say the face of the barn is in blue. It should probably be red, huh, because it's a barn, but whatever. So let's say the face of the barn is in blue. So it draws all the white pixels first, then it draws over it in blue. And this is something called the Painter's algorithm. Okay. That's not really used much anymore. We use today two different techniques that are very commonly used. One is called z-buffering. You might have heard me use this term before, z-buffering. When there's a z-buffer conflict, the z-buffer is depth. So on the screen, you've got x, which is horizontal. You got y, which is vertical, and y goes down, of course. In screen coordinates, the origin is here. That's 0, 0 in screen coordinates. And then you've got z. Z is depth into the screen. So in the viewport coordinate system, x is to the right, y is down, and z is in. So something that has a higher z value is further away. So what happens when we rasterize is we figure out every pixel that is in the roof, and we write down how far it is away. Like this pixel is -50, and let's do it in white because it's the roof. So let's say that pixel there is 50 meters away, and the pixel for the front of the house is 30. Let's use a non-neon color. Let's say the front of the roof is 30 meters away. 30 meters is closer than 50 meters. So when you draw a pixel onto the same place that a pixel exists already, it checks what's called the z-buffer. The z-buffer is a chunk of RAM. You're trying to write an RGB value at that point in RAM. There's already a pixel there. The z-buffer will say which one is closer. If you're trying to write a new pixel that is further away, it gets occluded by the nearer one. The nearer one stays. If you, however, you're trying to write one that's nearer than the old one, then the new color pixel overwrites the old one. And so if you've got multiple triangles all overlapping each other, the z-buffer will figure out how far away each and every part of those triangles are and draw the nearest pixel on all of them. And it works out really nicely. This has been the primary technique for doing rasterization for 40 years now. When the technique was developed, they actually said it wasn't useful because it consumed too much RAM. Like, who's got a spare kilobyte of RAM to throw around, you know? So they said it was incredibly expensive to use z-buffering. You should use Painter's algorithm, because the Painter's algorithm, if you can sort all the triangles from furthest to nearest, you don't need to have a separate z-buffer to hold depth information on them. But nowadays we don't use Painter's algorithm very often. We use this, and so the z-buffer here shows you what's nearer and I guess darker, and what's further and lighter. And so if you ever try drawing something over something else, it will do a depth test. It'll do a depth test and say whoever is closer gets drawn. So here's a z-buffer conflict. If you ever draw two things at exactly the same distance away, you'll see flickering on top of them. And the reason for that is because the z-buffer is held in doubles, or floats maybe. And so there's rounding errors. And so even though all of these guys are, 5.2 units away, the black, the sky blue are all 5.2 away, Sometimes 5.2 will round up, sometimes it'll round down, sometimes you'll see one, sometimes you won't, you'll see the other. Okay. So that is a Z buffer conflict. And yep. All right. So that is Z buffering. And so what you do is you basically just go through every triangle. For every triangle, you say that pixel's white, that pixel's white, that pixel's white, and you write down how far away that pixel is. The barn is 50 away. The barn is, this pixel's 52 away. This pixel's 53 away. That one's 40. And then when you draw the front of the barn, it doesn't matter if you draw the front of the barn first or the roof first. It doesn't matter because every pixel has a R, G, B, A, and Z. Okay? And doing transparency is annoying also. Because if you've got a 50% transparent pixel here, then when you draw behind it, you actually blend them together. And so doing transparency is kind of annoying to implementing it. So, so yeah, do you guys understand Z buffering? So basically, for every triangle, you project it onto the screen, and you basically iterate across every pixel that triangle touches, and you write that color of the triangle. Again, computing the color is a lot of work, because you got material and light and the normal and all that other stuff, parallax mapping, all that stuff. But you get a color. At the end of the day, you get a color. And so I'm going to draw pink at the screen, 50 across, 20 down. I'm writing pink, and that pink pixel is 50 meters away from the camera. And then maybe 10 different triangles will all try writing to the same spot. And maybe the green one is even further away, so it gets hidden behind the blue and the white, because every time it tries drawing a green pixel here, it's like, oh, the green pixel, well, that thing is 2,000 meters away. It's 2 kilometers away. So 50 meters is closer than 2 kilometers, so it draws the white. But for here, 30 meters is closer than 50, and 50 is closer than 2,000, so it draws the blue, right? And so you can have many, many overlapping triangles. Maybe you've got a magic thing that's in front of the barn here. It's a magical effect, whatever. And that's only 5 meters away. Then that'll draw on top of the 30, which will draw on top of the 50, which will draw on top of the 2K. Are GPUs optimized to calculate distance or something? I feel like all of those distance calculations are a bit much. So what we're talking about there is what's called a projection. So you've ever heard in psychology when somebody says, you're projecting, man, it has nothing to do with this. So what happens is you've got a triangle that's in the world, and this is at world location. We're in world coordinates now. 5,000, 2,000, negative 1,000. And this one's at 5,001, 2,000, negative 1,000. This one's at, 5,000, 2,001, negative 1,000. So these are like big numbers, because this is a very small triangle. It's only a centimeter big-ish. But it's 50 meters away from the origin. So, given where the camera is, maybe the camera's over here, looking in this direction, there's what's called a projection. So it projects from world coordinates into screen coordinates. And so it takes this triangle, given the view frustrum, right? You got a view frustrum, near clipping plane, far clipping plane, and it's going to say, okay, translate this triangle from world coordinates into screen coordinates. Okay, and so if this and the pixels don't have to be the same depth away, right? So this corner could be 100 meters away, this corner could be 0 meters away, and this corner could be 50 meters away, right? And so it'll have to do a lerp between the different pixels to compute how far away each one of these pixels is. Then if you got another triangle that's overlapping it, for every pixel of the overlapping triangle, that triangle gets projected onto the view coordinates as well. And for each one of these overlapping pixels, it sees, based on the lerp of the two basis vectors of the triangle, if that spot is closer than the other one. And if you move the camera, right, Muya? Like if I move the camera around to the other side, right, then it might very well be in the opposite direction, right? So which triangle gets drawn first depends on if you're on this side or if you're on that side. And so every triangle gets projected onto the screen coordinates. And to answer your question, yes, it is optimized to do that. So all of this stuff is linear algebra. It's the kind of stuff we talked about in IS50A. And it does a linear algebra transformation that takes a triangle from world space here on the left, and it transforms it into the viewport here. Okay. And this is the thing here. That's how you do a projection. Okay. And then for every, so once that triangle has been perspective transformation. Why is it in German? It's interesting. Local Welt Betrachter. So once you've done the perspective transformation, then it's going to get clipped. Then it's going to get rasterized. So rasterized means given this triangle here on the screen, go through every point of the triangle. Every pixel of the triangle, go through it and draw to the Z buffer the depth, and draw to the color buffer, the output buffer, the pixel color. And then when you rasterize this triangle here, it says for every pixel within the boundary of the triangle, pixel, 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 write the RGB values to the output buffer, the screen buffer, and write the depth there to the Z buffer. And the Z buffer will determine which one gets drawn on top. Does that make sense, William? So for every pixel within the triangle, draw the color and the depth. And if there's another triangle there already, it will Z buffer to determine which color wins. Okay. And if it's transparent, then it gets complicated. Right? Because the order of operations matters when you're doing transparency, right? Like if you have a 50% transparent and you've got an object over here, and so it's like, okay, this one's red, this one's blue, draw it as purple, cool. Now let's say you put a 100% opaque thing in between the two of them. You can't use that purple color anymore because it's not valid anymore because you can't see the thing on the backside. So yeah, transparency gets complicated. So yeah, it gets annoying with transparency. So let's not worry about it. Not worry about it. Okay. So how do you rasterize a line? So if you wanted to rasterize a line, like you're going to have to do for this homework assignment, you're going to have a starting x and y. You're going to have an ending x and y, x2, y2. And so what you're going to do is you're going to calculate the rise over run. All right, you guys know how to do that from algebra. And step multiply by 1 over and over again. And figure out your new x and y location. And draw that in white. And then multiply it by 1. And draw it in white. And multiply it by 1. You know, and you just have a thing that you keep adding the rise and the run to it. And yeah, and then that'll end up drawing each of the points in between, or rather, you multiply. Let's see, you go. You go right 1 pixel, and then you figure out how many pixels up you have to go based on that. Yep. And if you want to be intelligent, then you can do subpixel coloring. So rather than having square, square, square like that, you can have these squares be a little bit colored. So if the line runs like this way or whatever, then this one will get a little bit of white. You don't have to do that. Just basically starting at this row, ending at this row, move right one column at a time. Sorry. Starting at this column, ending at this column, go right 1 column at a time, and just move up a number of rows equal to the rise. That's it's not going to look good. It's not going to look good, but it'll work. I would actually figure out which one is bigger, either the run or the rise. And if the run's bigger, I would go right 1 run at a time. And if the rise is bigger, I'd go up 1 rise at a time, and that'll give you a better looking line. So that's rasterization. It's just drawing pixels onto the screen. So given an endpoint and an endpoint, which pixels need to be turned white? That's all rasterization is. Putting pixels on the screen. So for the homework assignment, you're going to have a bunch of things, and you're going to have to draw a line between them. So whenever you triangularize, you're going to draw a line between them. You don't have to fill it in. You don't have. Well, maybe that could be fun. That could be extra credit. So rasterize the triangles. So actually draw all the points in between the triangles. Different colors, maybe. You can see it. Otherwise, it's all going to be a solid blob, right? So have a different color for each triangle. But all I'm expecting you guys to do is just have a... Oh, look. The touch... The pen actually works on it.
What? It does?
Yeah. So just draw the lines. And so like I said, just figure out which one's bigger, the rise or the run, and then loop. If the rise is bigger, it's like this. If the rise is bigger, go up one row at a time and figure out what the column should be using the powers of algebra. If the run is bigger, like here to here, like here to here, then go right one column at a time, figuring out what the row should be. And that'll give you a okay looking line. It's going to be alias to hell. It's not going to be pretty, but it'll be sufficient for the assignment. Okay. Now, do you guys want to know what the alternative is to Z buffering? Ada, do you want to know?
What?
Do you want to know what the alternative is to Z buffering, Ada?
Yes.
You do. She wants to know. Do you guys want to know? Remember, you meant to talk about a semester in-game project. Yeah. So, so we got 8 weeks left. I'm going to want you guys to put together something cool for the end of the semester. I want you guys to work in groups. It's good for you guys to work in groups. We've talked a lot about computational geometry. If you want to incorporate something like that, like I know Walker's got his Poisson disk thing, which is pretty cool. But also landscapes, animations, maps. We've talked about maps a fair bit. We're going to need to talk about multiplayer. That's a big thing. And maybe AI. Those are the two big learning points we want to get onto. And maybe blend spaces. Blend spaces are kind of important too. Blend spaces, AI, and multiplayer. But that's one idea. You do it on Unreal Engine. Option 2 is you do it on the server. So once you have the ability to rasterize a triangle, which you could do in this homework assignment, rasterize a line, rasterize a triangle, you could actually construct I don't want to spoil it, ray tracing engine, because that is the alternative actually to Z buffering, is rather than, because with a triangle, the loop is this. You've got a triangle, what you do is you loop over every pixel within the triangle and you draw it. And so this scales badly. This scales badly because if you're, even after doing all of this culling, even after you've done backspace culling and level streaming and Frustrum Culling and all that stuff, it's still your workload is going to be equal to the number of pixels in visible triangles. Right? So if you got a lot of triangles in front of you and you can't cull them, and you've got a 4K monitor, that's a lot of pixels you're going to have to process. And graphics cards are fast at it. They can process billions of pixels a second and do Z buffering on billions of pixels a second. Like, they're good, but they don't scale well, right? What if, instead of having the work be proportional to the pixels in the visible triangles, what if the work was proportional to the pixels on screen? What about it? Scales a lot better, right? Scales a lot better. Because, if you have a really low triangle count world, sure, this is faster. Right? Sure. You got 2 triangles, you can rasterize them faster than looping over the whole screen, right? So, do you guys see this? So rather than looping over all the triangles that need to be rasterized, what if you could just loop over every point on the screen and figure out, using the power of data structures, for every pixel, figure out what color to draw. Okay. just imagine, like John Lennon, imagine that you could simply, you've got this farm. Here, let me redraw it down here. We've got a farm, and we got a roof on the farm. Got a triangle on the front of it. We got the camera looking this way. So what if we could just loop over every point on the screen and be like, and we got like some magical effect here in front of it, right? Like we talked about. And the roof is blue for some, or the front of it is blue. I don't know why. And the roof is white. What if we could just loop over every point on the screen and be like, ah, that point needs to be blue. Ah, that point needs to be white. Ah, that point needs to be white. Ah, that point needs to be magic colored. You guys understand? If you could do that cheaply, then your world could actually scale much better. You don't even need to use level streaming and all this other stuff. If that is a cheap thing, like if you just shoot a ray out of your eye, I don't know, like let's call it ray tracing, I don't know, or ray casting. Let's say we can shoot a ray out of that pixel, and that pixel flies forward and it hits this magic effect. Can you call your friends? Here you go. If you could shoot a ray out of that pixel and be like, okay, that's the front of the barn. Okay, that's the thing. Oh, that's the roof. If that is a cheap operation to do, then your world can actually scale much better than with Z-buffering, right? We've been doing Z-buffering for 40 years, and we're pretty good at it, right? But we now have hardware support, RTX on, right? There is now hardware support for doing ray tracing. And the support is in the terms of a data structure. You have to have a good data structure. So maybe this barn here is represented with a bounding box that looks like this. And so when the ray shoots forward, it hits that bounding box. Remember how we talked about that in February, right? We have this is a BSP here, but yeah, let's say you have a bounding box around a bunch of other boxes. And so you can do what's called a bounding volume hierarchy, right? You can do a BVH. And so like maybe this whole world, maybe all these boxes over here, the warehouse is held in one bounding volume, and then there's a smaller bounding volume holding these boxes, and then these boxes are held in smaller bounding volumes. It's a bounding volume hierarchy. And so it's very simple to see if a line touches a rectangle or a cube, right? And so what if that could be done in hardware? That's what RTX does. Okay. So what RTX is, the RTX cards, is it has hardware support for bounding volume hierarchies. So you can say, throw a ray out of my eye and tell me what I hit quickly. That's actually a very fast operation to do. So, so if you're doing Unreal Engine, it will do it for you. You can just turn on RTX and it does it for you. If you're doing one thing I'd really like to see somebody do is in text, you can do a ray tracer. For every pixel on the screen, shoot a ray through the world, intersect with the bounding volume hierarchy, see what's there, and be like, oh, that's supposed to be the front of the barn. It's blue. And you can actually render, and if you increase the resolution of PuTTY, you can render a 4K image, fully lit, all this stuff using ray tracing. And it's not actually that hard. It's not actually that hard. If you're not doing lighting, this is actually really, really easy. You know, you have a bounding volume hierarchy, which is just a cube. And so you just use, you know, that ray, and you're like, okay, that ray does hit the bounding volume hierarchy. All right, well, okay, it hits the front. Okay, the front wall is white. Okay, draw a white pixel there. All right, do it again for the next one. So for every point on the screen, you shoot a single ray out. And if you're not doing lighting, that's it. This is a very fast operation. It's order log n, where n is the number of objects in the world. So if you have 1 billion objects in the world, right? If you have 1 billion objects in the world, which would cause any rasterizer to choke and die. If you've got 1 billion triangles in the world, You know, think about all the pixels on all those billion triangles. You're trying to render it every frame, and all of those are not culled, right? It will cause the rasterizer to cry. However, 1 billion, 1,000, 1 million, 1 billion, if you take the log base 2 of it, log base 2 of it, it is 30 operations. So for every pixel on the screen, it is 30 operations to find the triangle you're going to hit. And so in a 4K in 4K resolution, let's do the math on this. 4K resolution, 3840 times 2160. Okay, 840 times 2160 times 30. It is 250 million operations. Easy. You don't even have to do Z buffering, because that operation is going to give you the closest thing to the camera. You don't even have to Z buffer it. You don't have to overdraw triangles on top of triangles on top of triangles on top of triangles. Overdraw is a big problem because you're wasting all that time redrawing the screen buffer over and over again. And so if you had a billion triangles and each triangle is maybe 1,000 pixels big, then you're talking about 1 trillion pixels. And with ray tracing, you do it in 250 million, right? So 4,000 times faster, right? If you're not doing lighting. How did rasterization get invented before ray tracing? Well, first of all, there's no hardware support for ray tracing until recently. And traditionally, ray tracing has been slower. And the reason why ray tracing is slower is because, you know, not having hardware support. You know, this is a highly optimized thing, and you could keep your frame rate up by just simply reducing your triangle count, right? And so with ray tracing, the problem with it is when you want to do lighting, and doing lighting correctly gets expensive. And so what happens is that when you hit something, you will scatter multiple other rays off of it. So usually if you have the sun over here, what happens is if you want to shadow this, you shoot a ray. Oh, it hit the barn. Okay, I'm going to try shooting a ray at the sun. Oh, I hit the roof. I can't see the sun. I'm in shadow, and it draws pitch black. So for every light you have around you, light. For every light around you, you cast a shadow ray to see if you can see that light. It's naive implementation, but that'll give you an idea. So it goes up proportional to the number of lights you have in the world. So if you have 10 lights, your frame rate drops by 10 times, right? It's a problem because lighting is nice, you know. And so maybe you do some things like you have some data structures that say, all right, if that light is too far away, I can't see it, you know, things like that. Plus other pixels can emit light. Yeah, bounce lighting. Ooh, and here's where ray tracing really gets complicated. So let's say that there is a light underneath the leaf of the roof here, and so that has fully lit the underside here. This light, and you hit the front of the barn, and the front of the barn shoots a ray up towards the sun, and it hits the roof instead. Rather than being black, it should pick up the light from the bounce. And so you have what's called global illumination, and global illumination is hard. There's actually a very beautiful algorithm called the lighting equation that tells you how to solve it, and it is gnarly. But basically, what you do instead of all this stuff is, yeah, you shoot shadow rays to see if you can see global illumination. You shoot shadow rays to pick up direct lighting, right? So for any sort of directly lit pixel, like let's say you shoot a ray and you hit the wall here, that'll shoot a ray up towards the light. I can see it. I'm lit, and how much lit am I is based on how far away I am from the light. In this case, it's got fall off. For sunlight, there's no fall off. It's pretty easy. And then if you want to do reflections, now if you hit a mirrored surface, you cast random rays out based on the angle of the surface and its roughness. And so you cast rays out this way, and then those rays will cast rays out that way, and you have to have a maximum bounce distance. Otherwise, two mirrors will infinitely loop, And so you cast a ray out, and the ray shatters into other rays, and those rays shatter into other rays. And that's why it takes a long time to make a nicely looking ray traced image. That's why ray tracing is used traditionally in like Pixar to make nice movies, because you can sit there and spend all night shooting more and more photons at the screen, picking up more and more accurate reflections and accurate lighting and things like that. If you're in a game, though, it's not practical for a game, right? And so the new thing with RTX is that the hardware is going to accelerate these things, and you can limit how many bounces you have, and when you randomly cast rays around, you actually don't get a very good answer. You will get you'll get actually a very noisy Quake 2 global illumination RTX. You'll actually get a very poor looking image, and so then you have to filter. You have to filter the results. Let's see if they have any pictures of this. Here's the running time, right? So with no global illumination, you get 140 frames. With low global illumination, 110, medium, high. So there's a big, cost on this, right? So let me see if they have... Yeah. And so here you've got sunlight coming in from this hole in the roof, and so that's brightly lit. And then this pixel here will pick up light from that pixel there. And then this pixel here will pick up light from that pixel there, right? And these things are emissive surfaces, so they're emitting light also. And so, RTX on versus normal. And so it'll globally illuminate a scene, but it looks garbage until you filter it. Look at that frame rate. Oh, that's based on... That's based on resolution. Yeah, this is what it looks like. Okay, cool. So this is what it looks like when you actually do global illumination. So you cast out a ray. Hang on one second. You cast out a ray, and it scatters rays elsewhere, and they pick up color from the random things they hit. So you can see we shoot a ray at the floor, and then this ray randomly bounced up into the orange sky, so it's orange. This one, it randomly bounced and hit a wall, so it's brown. This guy here randomly bounced and hit an emissive surface, and it's green. This is what you get raw out of doing ray tracing, because it's random. You don't have you're in a game. You don't have all day, like in Pixar, to send thousands of rays out to get a nice looking reflective global illumination thing. Instead, and you can see here, it bounced and hit the light, and it probably has some direct lighting there as well. And so what you have to do is you have to filter it, and so the filters will turn this into a nice looking image. Yes, girl.
Can I ask with something like texting to ask Shoshana's dad if I could call her into a call with me, and I said,
yeah. And so you see after it filters, it looks really nice.
Bye-bye.
Goodbye, girl. So that's basically it for today. We can talk about ray tracing some other time. But that's kind of the nutshell of how ray tracing works. And so it's really an alternative to using the traditional graphics pipeline. And the traditional graphics pipeline has been very, very highly optimized over the years. Games engines and hardware, we have a lot of experience doing it. If you turn on ray tracing in Unreal Engine, it'll crash a lot. The performance is not very good. It looks very noisy. There's lots of flickering pixels and things like that. So this is the newness, right? But because of this one little fact here, you can RTX actually has a pretty high ceiling to go. Like as we and not me, but like we the industry, not me, NVIDIA gets better at figuring out this. There's actually a huge upside to this, because you can throw way more triangles at the world than we've ever seen before. And if we have a fast data structure to access it and fast ways of doing lighting, and we can hardware accelerate all that stuff, then we can actually get very beautiful images that are faster even than this. Okay. So your dream job is working on game or rendering engines, yeah. Then start here. Make a ray tracing engine. inside of, maybe we'll do both. I don't know. Maybe we'll make a ray tracing engine inside of Putty, and then because we can do this in 4K. Nothing's stopping us. There's no law. There's no law saying you can't run Quake 2 inside of a terminal. Inside of a terminal, getting 0.05 frames per second because there's no frame buffer. You know, no one's stopping us. Maybe we'll do both. I don't know, but yeah. So start talking, form groups of like 3 to 4. Talk about what you'd like to do in Unreal Engine and or in Putty, and yeah, all the stuff that I've been trying to teach you guys, like computational geometry. It all ties together, right? Because you can't do triangularization maybe without having a concept of holes and intersection testing of points and triangles and stuff like that. Like there's a method to my madness. I'm not just throwing random stuff at you guys. You know, landscapes and animations are important. AI is important. Network is important. We'll get to those. But I do want to jump back into this because this will be a good intro for you guys to do ray tracing. So triangularization, rasterizing lines turns into rasterizing triangles, which turns into ray tracing. Okay. That's it for today, guys. So I will push out the homework assignment. Again, if you don't know how to C++ program, partner with somebody that does. Don't wait to the last minute. Don't play Valheim. Sorry. Risk of Rain. I was watching Walker and GT play Risk of Rain the other day. 6 o'clock in the morning. Who's up that late? Oh, wait, I am. I'd actually woken up earlier. Fell asleep at like 8 that day. All right. So that is it for today, guys. I will see you guys.